Let me share the screen. Is it, visible? Okay, so we briefly talk about duality. So I think Reza already mentioned this, but I will just go a little more into it. So given a planar graph with an embedding on the plane, we call it a plane graph. So uh, so together with the embedding, we call it a plane graph because it has also well-defined phases, right? What are the phases we know? Because if you take any planar graph, it could have several different embeddings where the phases could be different. But to define the dual graph, we need the phases also to be clear. What are the phases? Okay. So given a planar graph, for example, in this picture, you have this planar graph with an embedding, right? And we have these phases, like let's say F1, F2, and F3 are the phases. Now, in the graph, what we do is that we assign, so we define a new graph where the phases of the plane graph become the vertex set, right? Or associated to this, we can define vertices. So let us say that F1 star is a vertex now, right? In the dual graph, F1 star is a vertex, and which corresponds to the phase F1, and F2 star is a vertex which corresponds to the phase F2, and F3 star is a vertex corresponding to the outer phase, which is the phase F3. Then what we do is that, like, if corresponding to each edge of the original graph, we define an edge in the dual graph. So how do you define the edge in the dual graph? Let us say that two phases, if an edge is incident to two phases, let's say Fi and Fj, then we draw a line or an edge in the new graph connecting F1, Fi star and Fj star. Okay. So we basically can, like once you have this embedding, we can basically draw it as follows. So if F1 star and F3 star have this edge as, in common, right? So we can just draw this edge because, F1 star and F3 star shares this edge. But it also shares the other edges like this. For example, it shares this edge also, right? It shares this edge because this is the outer face, and even this edge, right? So we have parallel edges in this. So the dual graph need not be a simple graph, right? It could have multiple edges, and then of course F3, this edge, for example, this edge, for example, right? If you look at this edge, you know that F3 is the only phase which is incident to, but it has, let us say that F3 with itself, so we can get a loop there, right? So you can see that cut edges naturally become loops because cut edge is only incident to one phase. And then F3 and F3 star and F2 star, again, it has this neighbors, so I can draw this, right? So now what we get is a graph we can see that the number of edges of this new graph is exactly equal to the number of edges of the original graph, because for every edge we define a new edge, right? So, so we get this graph, and we call this new graph as the dual graph of the plane graph that we started with. Okay. So to state this in words, so let G be a plane graph having the vertex at V, and let's say the edge at E, and the set of faces is denoted by F. Now, to define the dual graph, let's say usually denoted by G star, we define vertices corresponding to the faces, right? So each face F, small f, we define a new vertex called F star, which is in the vertex set of G star, right? And corresponding to each edge E, right, we define an edge E star, and this E star is basically defined as follows: if F star and G star are two faces, not necessarily distinct faces of I mean, F and G are two distinct, not necessarily distinct faces of G, then F star and G star are two vertices in G star. They are joined by the edge E star if E is the edge which lies on the boundary of F and G. So that is the dual graph. G star is called the dual graph of the graph G. It's a plane graph G. So here is another example. You have the graph G, which is represented here. Now, if you look at G, we have two faces, F and G, right? And therefore, we have two new vertices, two vertices in the graph G star, the dual, which are these two. And what about the adjacency? So, corresponding to E1, E2, and E3, we have E1 star, E2 star, and E3 star. And since all three lie on the boundary of F and G, we have these three parallel edges, right? E1, E2 star, and E3 star are parallel edges. And the edge E4 on the other hand lies only on the face G, and therefore we get a loop corresponding to E4 star. So dual graph. Now let us look at this graph as our starting graph, which is again has a plane embedding. You can see it, right? And if you look at the dual of this graph, G star, right? What is that graph? Okay? So you get another graph. Let's say each face of this graph, let's say it's P, Q, R, and S, right? So these are the different faces one can see, right? Now take these faces, right, and they become the vertices P, let's say P star, if you want P star. I should put P star maybe. P star, Q star, R star, and S star are the vertices. And then we draw the edges corresponding to, right? So E3 star becomes E3 star star, right? Which is an edge between P star and Q star because it is in the boundary of P star and Q star. Similarly, you get all the other edges, right? So you get this graph, which is the dual of the dual graph, right? And in this case, you can see that they happen to be isomorphic, right? So G and the dual of G star happen to be isomorphic. So one can think about this question like, is it always the case? Are there exceptions? Or when can you say this is going to be the case? Okay, so here are these questions that I want you to think about, right? So given a graph, plane graph G, is it always true that the dual of the dual is isomorphic to itself, right? To the graph G, right? So dual of the dual of G is isomorphic to G. Is it true? So you can, you can approach it like, you can either say that it is true for all graphs, or you can say that for certain classes of graphs it is true, otherwise it is not true. So when it is true, so these questions you can think about. I want you to think about this. And so if you look at some examples, you will get a pretty good idea. So now, consider a planar graph, let's say, and let us look at two embeddings of this planar graph, right? You can have several embeddings possibly, right, for planar graphs. Let us say H and H dash are two embeddings of the planar. Is it always true that H star is isomorphic to H dash star, right? So you take the same planar graph, it has two different embeddings, right? So we have plane graph H and plane graph H dash, which are embeddings of G, I mean some graph G, let's say. Now you look at the dual of corresponding plane graph, right? H and H dash. I mean, it is of course the dual of the same graph that we are talking about, right? I mean, the planar graph is the same, but the plane graph is different. Now is the dual going to be isomorphic? So what do you think? If it is true, show an isomorphism. If it is not true, show that you have contraction, right? So here so suppose a graph is isomorphic to its dual, right? A plane graph, right? So when I say this, it is basically plane graph. Right? So a plane graph, maybe a plane graph. Then this graph is called self-dual. Right? Now here I am giving you two examples, right? Two graphs which are self-dual graphs, right? Which means that if you look at the dual of the first graph, it will be isomorphic to itself, and the dual of the second graph, it will be isomorphic to itself. Okay, this is very different from the previous question that we were discussing, right? We are looking at the dual of the dual, right? That is a different thing, right? So here we are talking about the graph, I mean the plane graph, which is going to be isomorphic to its dual. So now, one thing you can think about is that are these two the only graphs, or can you find more graphs? Or in fact, can you find infinitely many graphs or not? Or there are only finitely many of them, right? So you can try to see whether there are infinitely many graphs which are self-dual, or only finitely many of them can be. Then show that if a graph is self-dual, then the number of edges in G must be equal to twice the number of edges minus 2. Then third question is to find an infinite family of graphs that are self-dual. Okay. Now the fourth question is to show that the dual of a plane graph is always planar, and you explain why. Because these are good questions that you should think about. So is the topic clear to you so far? Okay. So we defined the subdivision of graphs sometime before, I believe, right? So recall that a subdivision is basically replacing some edge with a path of length 2. Right? So you take an edge and then now say that, okay, instead of this edge, I will have a path of length 2 there, right? Or basically introducing a vertex in the middle of the edge, right? So you basically subdivide the edge. That's why it's called subdivision. Right? So the example here shows that the edge E in this graph is replaced with a path of length 2, introducing a new vertex, let's say 5. Right? So we get this graph. So this kind of operation is subdivision. You can do it many times. It will still be the subdivision of the original graph. So we say if you can obtain a graph by subdividing edges any number of times, then the resultant graph is called the subdivision of the original graph that is. So here is another example. We have the graph G, right, which is a k4 minus an edge, and then in this graph we have subdivided the edge 2, 3 once. So you get this this path here, right? Then we subdivided the edge 3, 4 two times. Right? So first you subdivide once, and then you subdivide one of the edges again, right? Then you get this one. Similarly, subdivide 1, 4 three times, and 1, 2 subdivide once, right? So you get a graph G dash, and G dash is called a subdivision of G. Now, so we are talking about planar graphs, right? So what happens if I take a graph and subdivide the edges? Right? Can it affect the planarity? I mean, can a non-planar graph suddenly become planar by doing the subdivision, or by subdividing edges, can a planar graph become non-planar? What do you think? Anand? Yes. Chinmay?
Cannot become non-planar, but non-planar can become planar. I think non-planar can become planar, but I'm not sure.
Okay. What about someone else? What do you think?
Sure.
Non-planar also can't become planar. Sorry.
Why?
Deleting will do something, but subdividing won't.
So, can you tell me why?
No, not right. I mean, not what I thought. Actually, a concept of what the complete edge to 4, then subdividing 4
Mm-hmm.
makes that a planar. Like, you have to redraw it somewhat, but yeah.
Well, what?
2, 4, it's even 2, 4, it's still having 2, 4, it's still planar.
Yes, it is.
Exactly. So that all. So,
And what? I cannot hear you. I mean, I cannot hear you clearly. I could hear some sound. Sanjana, what do you think?
it doesn't make any changes, sir. Even if you subdivide, there won't be any changes.
Why?
Like as you were saying, in case of 2 and 4, because it was planar only, sir.
No, we don't want examples. We want the reasoning, right? We want to see why it cannot change planarity or why it can change planarity. Right? So we need some reasoning like that.
Right. Yeah. So if edges AB and C cannot be drawn on the graph without crossing each other, then
Okay.
if you subdivide it, then at least one edge in the subdivision will cross one edge in the subdivision of the other edge.
Why?
And if you open that up, there will be some other pair of edges that will cross each other.
Why? Okay, I mean, like, so you have this feeling that it is not possible. So how do you say that it is actually the case, right? Well, what is basically an embedding of a graph, right? So embedding of a graph is that you basically assign vertices to points on the plane, right? And then you are corresponding to each edge. Now you are saying that there is a curve or a line segment, right? Which connects this point. Right? Now, if you look at this, topologically, right? If you introduce a vertex on an edge, it is essentially not doing anything, right? It is basically saying that claiming that one of these points is now a vertex. That's all we are saying, right? So if there is an originally a connection from so we are not deleting any of the original vertices in the graph, right? So they are still there. Now what we are saying is that okay, so u to v there was an edge. Now if you introduce several vertices on this edge, right, it is only saying that okay, there is a path from u to v now, right? So this path also must be a continuous curve, right? I mean, not necessarily, well, you can draw it non-continuously, but I mean, what I mean is that connected, curve between these 2 points, right? So, essentially, we are saying that there is no way to work around this, because if it is going to pass from one phase to another, right, it has to cross one of the edges, right? Because it's basically a path which is on the plane, right? So we can of course make it more formal, but I believe that you got the idea, right? So the subdivision cannot affect planarity. So this gives a handle to think about planarity, and can you try to reduce the non-planarity to some cases, right? Some simple cases. That Kuratowsi did, right? So we observe that subdivision does not affect planarity. That is, G is planar if and only if every subdivision of G is planar. Now, so what Kuratowsi did is that he claimed that, I mean, he proved that actually a graph is planar if and only if the graph contains no subdivision of either the graph K5, which is the complete graph on 5 vertices, or the graph K33, which is the complete bipartite graph on 3, 3, right? So these two we have already proved to be non-planar. If you remember, we have already proved these two graphs are non-planar using two different methods. One is using Jordan curve theorem, and also using the Euler identity, right? So you remember the proofs, I believe. So can we get it on, right? Now this says something, right? It's like we are saying that okay, you have infinitely many planar graphs, but and infinitely many non-planar graphs, but all of this now we can say that okay, the graph is planar if you cannot find a subdivision of either of these graphs as a subgraph, right, sitting inside this graph. So that is why these two graphs are very important, and we basically proved they are non-planar in the beginning. So we want to prove this theorem, but there are several ways of proving this. The original proof of Kuratowsi is also a nice proof, but we are going to put this in terms of what we call minors. So I think we mentioned minors before. Let me mention it once again. So of a graph is basically a graph that one can obtain by by a sequence of operations like either vertex deletion or edge deletion or the contraction of an edge, right? So we saw what is contraction of an edge, right? We are basically taking an edge and then saying that okay, these two adjacent vertices are now identified to form a new vertex, right? So basically you in the embedding, if you are talking about not necessarily an embedding actually, I mean you can basically say that okay, you are making them closer and closer so that they coincide. So so you have this notion of edge contraction. I believe that we have defined this. If I have not done before, you should tell me now. Now, for example, so we can graph. Now, what we can do is that we can contract these blue colored edges. Now, I have marked here. So, I know that first, and I identify this vertex and this vertex. So, what happens to the edges? So of course, the other edges will all be incident to this new vertex, right? This edge will disappear because it is now contracted. We can now look at the graph where these two have become one, right? Then I do for each of the other edges, and I will end up in this graph, which is the graph on complete graph on 5 vertices. So K5, right? The complete graph on 5 vertices is now a minor of the Petersen graph. So Petersen graph contains a K5 minor. That's what we say, right? So if I can obtain a graph by doing these operations, then it's a minor, and then we say that Petersen graph contains K5 as a minor. It is not a subgraph, for example, right? So you see that if you look at K5, K5 cannot be a subgraph of Petersen graph because there is no vertex of degree 5 in Petersen graph, right? All the vertices are of degree 3. But the minor can have higher degree than the original graph. On the other hand, if you look at subdivision, right? Subdivision, you cannot increase the degree, right? You are only going to introduce vertices in the edges. So basically, you cannot increase the degrees. Okay. So now we look at this point. So you have G with a vertex set V. We partition the vertex set to let's say V0, V1, V2, etc. Vk. Okay, are there any questions so far? Okay, so you partition the vertex set into let's say V1, V0, V1, 2, etc. Vk, and then look at V1 to Vk, right? Not V0, right? So I want to have the partition be such that each of these V1, V2, etc. Vk must all induce some connected subgraphs of G. Okay? So I don't want the induced subgraph to be disconnected. So if you look at the vertex set V1, just removing all other vertices, you will get a graph which is G of V1, right? And I want G of V1 to be connected, right? Removing all other vertices, I should have this to be connected. Similarly, for each of the VAs from V1 to Vk. But V0, I don't care, right? Now, take such a partition. What you do is that you delete all the vertices in V0, right? So delete all the vertices in V0. Then we know that G of V1, G of V2, etc. are all connected subgraphs, right? Now, if a graph is connected, you see that you can basically, you contract all the edges one by one, you will end up in a single vertex, right? because when you contract, two vertices become like contract an edge, they become one, right? Then you contract one of the other edges. Because the graph is connected, you can keep on doing this till you get a single vertex. So I now contract each of the subgraphs G of B1, G of B2, etc., G of Bk to single vertices. Of course, the other adjacency will be remaining as it is, and then we get a graph, right? So by doing this. So this graph is a minor of the graph. In fact, every minor one can see is obtainable this way. So here is an example. I claim that this graph has K33 as a minor. So how do you show that this has K33 as a minor? So of course, one easy way is, of course, if you, not necessarily always possible, right? If you can find a subgraph which is isomorphic to K33, that is immediately going to give you, a minor, because every subgraph is basically a minor because you delete only the vertices and some unnecessarily edges, you can end up in a graph, and therefore it's already a minor, right? So every subgraph is going to be a minor. Now, if you cannot find a subgraph, then you have to do something else, right? So we can try to do this procedure that we just mentioned here and see whether you can find K33. So I'm going to do the following. Okay. I put this into, let's say, some groups. Okay. Okay. So I put this into these groups, and then what I do is that I think this. Yeah. So I put this into these groups, and then what I can see is that each of these vertices in this domain now, right, are all going to be graphs, right? And I have these blue vertices, which define some subset of remaining vertices, which I say is V0, and each of the other ones I will call as V1, V2, etc. Right? Now what I do, I am going to delete the vertices in V0. Right? And I contract each of these into a single vertex. And now one can see that, right, this graph that we have obtained is precisely K33. One can show that in fact this will form one side and the other thing will form another side of K33. So this way we can see that K33 is a minor of this. Right, essentially, like if you want the deletion operations, we have deleted the vertices, right, in V0, right? Then we have contracted the edges in each of these components, right, to become single vertices, and therefore we have a deletion contraction operation, right, sequence of operations which will end up in this. So we get a K33 minor. Is that clear? Okay. Now, if a graph f is a minor of G, we write f minor of G in this way, right, using this symbol. And suppose H is any graph, and we say that H is a minor of G if H has a minor which is isomorphic to, G has a minor isomorphic to the graph H. So this way we can, so when we say, H is a minor of G, I don't say that H is sitting inside, right, G, but it's basically a graph which is isomorphic to H is a minor of. So if H is a minor of G, then H is also planar. So why is that? The very minor of a planar graph is planar.
There won't be any explosions.
Why is that? So we are so we are contracting edges, right? Not just deleting, right?
Okay.
So you have to tell me why. I mean, there won't be any edge closing. You have to justify that, right? See, if G is planar, then G has an embedding, right? So planar embedding. So you look at the plane embedding of the graph, and then so if you do that, you do after this embedding is made, right? So you make the embedding, then you delete some vertices. Of course, the embedding is still valid, right? We are not going to change anything. Now we have to show that the contractions will not change planarity. How do you do that? Well, you have embedding, and if you want to contract an edge, all you have to do is that basically we know that once you draw an edge, nothing is going to cross it, right, in the embedding. So therefore, I can basically make the length of the edge shorter and shorter, so that this edge becomes a single point. Right? So the other vertices in the neighborhood becomes adjacent to it, and therefore it becomes identical. Because nothing is crossing this edge, this operation is not going to affect the planarity of the embedding, right? That the new embedding that we have obtained by moving these two vertices closer to each other. And this we can do, and hence you see that the minus or must be also planar. Now, Wagners theorem says that a graph is planar if and only if it has no K5 or K33 minor. So these are called Kuratowsi minors because Kuratowsi initially proved that K5 and K33 must be subdivisions. Now Wagner basically showed that they can also be framed in terms of minors. Okay. So you start with any graph, and if you show that it's not possible to obtain K5 or K33 as a minor of this, then the graph is still planar. So we want to prove this. In fact, this this theorem is one can show it's equivalent to Kuratowski's theorem also by doing some additional steps, but we will not do it at the moment. But we want to prove this, and to prove this, we need a lemma. Okay, something about three connected graphs. So this lemma we are going to prove today. So the lemma is the following: you take any three connected graph. Right? So we already studied about graphs and connectivity, and we proved Menges theorem, etc. Right? So you are familiar with this. So you take any three connected graph. So the graph is three connected means that you need to delete at least three vertices to separate, right? Any pair of vertices, right? So therefore, like take any three connected graph which is different from complete graph on 4 vertices, right? So any graph different from K4, which is 3 connected. Then the lemma says that you can always find an edge. If you contract that edge, you will still find the graph to be remaining graph to be 3 connected. Okay. So any graph different from K4, you can contract so that the graph becomes graph remains 3 connected. There is some edge. You are not saying that every edge you can do this, but one edge you can find with this property. So how do you prove this? So we start with an assumption that there is no such edge. Okay, that every edge if you delete, not delete, like if you contract, will result in a graph which is not 3 connected, which means that it has a separating set of size at most 2. So, so we start with the assumption that G has no edge whose contraction results in a 3 connected graph, right? So then what do we do? 1 second. Sorry. So if what did I say? Yeah. So there is no edge whose contraction results in 3 connected graph. So therefore, you have a separating set of size 2 after the contraction. Right? So if you look at G contraction xy, then it has some separating set of at most 2 vertices. Now it cannot be just one vertex, right? Because we are just contracting 2 and the graph originally was 3 connected. So therefore, we need to remove at least one more, right? So therefore, you need to find a separating set means that you need to have remove at least 2, right? Now, so that now if you want to remove just 2 vertices, then one of the vertices one can show must be the new contracted vertex, right? Because otherwise the original graph also you can show contains a 2 cut, which is 3 connected, so which is a contradiction. So therefore we can see that since the original graph was 3 connected, the contracted vertex, the new vertex, let us call it Vxy, must be part of the separating set S that we are talking about, right? So the cardinality of S is actually equal to 2, and I already explained why. But yeah, so the separating set contains this new vertex and some other vertex. So this is true for every edge xy in the graph, right? So every edge xy, if I contract, right, any edge I contract, I will find another vertex, and this new vertex and the other vertex will be a separating set for the graph, which means that once you remove this, you have at least 2 components in the graph. Is it clear? So suppose you start with such a graph. So G, if you pick some xy, you will be able to find some vertex z, which is apart from xy, so that the contracted vertex Vxy and z is a separating set, right? Now look at the set x, y, and z in the graph, right? So I contract x and y, delete it, then you remove z, I will get a separating set. Means that if I remove x and y, right, and z, then again it is a separating set, right? So x, y, and z is a separating set, and because the connectivity was 3, it is a minimal separating set, because you cannot have any subset of this which is separating, right? So x and y and z is a separating set for the graph, right? Now If a separating set is minimal, then every vertex of the separating set must have neighbors to each of the components in the remaining graph, G minus T, right? So if you T is a separating set, look at G minus T has several components. If T is a minimal separating set, then every vertex of T must have neighbors to each of these components, because otherwise, apart from this vertex, I remove the remaining things. I will have this one component which has no neighbors to this, so therefore it becomes separated, right? So therefore, every vertex must have a neighbor in each component of G minus T. So now what we do is that, so we choose the edge xy with the following property, right? So we choose the edge xy and the vertex z such that once you, so this xy and z, we know that xy is an edge, then xy and z, another vertex z you can fix up, right? So that removing x, y, and z will have some components, right? So at least two components. Now we look at each edge xy and each possible vertex z that you can choose with xy, right? There could be more than one vertices who will disconnect the graph, right? So look at each of the possibilities and find or choose the edge xy and the vertex z such that the component, right, some component c, right, we are going to fix in G minus xyz is as small as possible. So we are going to fix some x, y, and z such that the component that remains, right, which is after removing x, y, and z, that is as small as possible. The cardinality is as small as possible, right? Okay. So this is how we choose the edge x, y, and z. I mean x, y, and the vertex z. Now what we are going to do is that we have this component C, which means that every vertex of this set T, right? This is, let's say, T. Every vertex of this T has some neighbor in C, right? In particular, the vertex Z has some neighbor, let's say V in C, right? So pick such a vertex B, which is a neighbor of the vertex Z, right? So we'll let V be a neighbor of Z in the component C. Now, because V is a neighbor, ZV is an edge, and in the original graph, right? Now, therefore, G contracted with ZV is again not reconnected by the assumption, right, of the graph. Otherwise, we are already done, right? If you can find one edge whose contraction results in three connected graph, there is nothing to prove. So, in particular, we know that G contracted ZV is not reconnected. So, we can find some other vertex called W, right? And this vertex W, if I remove with Z and V, we get another separating set. And this is separating. Now, again, each vertex of the separating set has neighbors to each of the components, right? Now, what we know about X and Y are that they are neighbors, right? Now, once I have the separating set, if X and Y are neighbors, they must belong to the same component, right? I mean, because they are already adjacent. So, since there are at least two components, there is some component of G minus ZBW which does not contain the vertex X and Y. Is that clear? So there is some component which does not contain X and Y. So D intersection XY is empty for some component D. Right? So we are going to look at this component D, and of course D has some neighbor right? Of the vertex V, right? Because V is part of the separating set, and V has neighbors in each of the components. So that in particular, it has some neighbor in D, right? So the vertex V has some neighbor in D. But now, look at all the neighbors of V in D, right? So look at vertex V and look at every neighbor of V that is going to be in D. I claim that they are all sitting inside the component C that we defined earlier. Why? Because C was a component and V was a vertex in the component, right? Which means that all the neighbors of V must be part of the same component, right? Because component means that it is connected. If you can reach V, you can reach its neighbors. So therefore, V and its small neighbors of in D are all part of the component C. Now, because D is a component and C is a component, D and C have some non-empty intersection, right? And therefore, the component D must be, sitting inside the component C, right? Because, everything which is reachable from V is in particular, right, part of this component C. Therefore, component D is sitting inside the component C. But this is a contradiction because the vertex B is not part of D, and therefore the size of the component D is smaller than the size of the component C. But our choice of C was such that it is the smallest such set, and therefore we get our contradiction. So therefore we prove that there must be one of the edges, of the graph whose contraction will result in a three-connected graph, right? Okay, I think we can stop today because. So any questions on this? If the proof is not clear, please get back to me. You can ask me now also.